This is water. It's 11:30. Okay, hello and welcome to Lab 4. Let's see, let's just focus on this for a minute. For this assignment, you will complete the implementation of the array-backed list data structure ArrayList started during class so that it supports nearly all the common and mutable sequence operations. For the ArrayList's underlying data storage mechanism, you will use the built-in Python list, constrained so that only the following operations, as would be supported by a primitive array, are available. And then it lists those 4 operations here. Okay, so recall for a minute being in your introductory computer science class, maybe that was in Java or C++. Working with an array is much more difficult in those languages than it is in Python. You can't do complicated slicing things. You can't do, there's no helper functions like extend. Tostrings are not built in, etc., etc. So what we've done here, and it's a lot, don't let it intimidate you, is create this class called constrainedList, which you will not do any coding in, and you can't, it's read-only, is create this class constrainedList, which inherits from the standard Python list. This is the syntax when you're defining a class for inheritance. That inherits from the Python list, but that for every nice helper function or one of the functions that you use on the regular when you're dealing with lists in Python, almost all of them have been restricted. All of these here inside of them, you see their whole definition is just to raise an error and say, I can't do this thing that you're trying to do right now. And so it's going to be your job inside this class definition here, ArrayList, to recreate those functions that we've decided in constrainedList you can't do. So this lab is so cool. I remember doing this myself for the first time and just thinking it's very, very interesting. I've never thought about how built-in functions like this actually get implemented. How you go from a standard array in a language like Java or C++ to this crazy capable, versatile, malleable list data structure that we get in Python. And this lab, you'll be figuring out how to do that yourself with some guidance, of course. So let's talk about these 4 things here. I'm going to put them in Paint real quick. Okay, so these are the 4 things that we can do. So if we imagine having an instance of the constrainedList class, let's call it CList. Our list here starts off empty, and the only way that we can grow it is by using the append none function. So appending something to the list, except the only something that we can actually append to the list is in an empty space in memory, right? And so we might imagine that that looks like this. And if we wanted to have more of those, we would do this over and over again, list.append none. And we might say, okay, cool, we have a few more empty spaces in memory, but they don't store anything yet. And we all know how indexing works in Python. This is at position 0, this is position 1, and this is position 2. And so if we did want to actually store something now in these boxes, we would execute setting and getting just as you do in Python. The only difference being that the index must exist already, 0, 1, or 2. We couldn't add to position 3. And the index must be positive. So if I open up a test notebook here, and I've put our constrainedList class in that test notebook, if I run this, and then I'll create an instance of the constrainedList class called CList. So the only thing that I can do to grow memory, or mimicking this here, is to say CList.append none. And I actually want 3 of these, so I'm going to run this 3 times up to 66, right? 1, 2, 3. Oh, up to 72, my bad, from 69. And so now we can think in memory of this structure existing. Yeah, a standard Python list, if we just have some list equals 9 times 3, then we can take a look at what this list looks like. and right now it's got 3 nuns in it, and that's exactly what our CList has. Now if we were to try and look at what CList looks like, we'll get an attribute error. Constrained lists do not support stringification. That's one of the errors put in here on purpose. Constrained lists do not support stringification because you'll also be building that function. You'll be building a function that outputs what your list looks like right now in memory, or a representation of it, which is what we got here. Okay, so now for this one, we're doing this in a strange order, sorry. So now for this first thing that we can do, we can of course get or set almost just like we can do with a normal Python list. So if I create a list that has some things in it, we'll say 1, 2, 3, 4, 5, just a simple list, indices 0 through 4. There are all sorts of operations I can do on that list, and the most basic of those is getting and setting. And so I can say, what's the list at position 3, and we'll get 4. I can say, what's the list at position 0, and we'll get the first item in the list. But the other thing that we can do is say, I want the last item in the list, and we have a special notation for that, as you might remember, in Python, where we can say -1, and there's negative indices all the way back to the beginning. But we don't have any of that with constrained list. So right now, again, we can't actually see what's going on inside constrained list, but we can imagine that right now it looks like this. We've got 3 empty spaces in memory. So let's populate that. We could say CList at 0, we want to be A, 1 is B, position 3 or index 2 is C. So now we can imagine that in memory we have A here, B here, and C here. And that may seem pretty basic, but I thought it'd be helpful to go over explicitly what the functions that we do have available for us via constrained list are. So we've seen that we can do getting and setting, and we've seen how to take a new box in memory, how to take an empty space in memory, and we can also, of course, get the length. If I say call length on CList, it will return that for me, and of course I can delete the last item in CList. So I can say I want you to delete this here, and I can show you that that is true if I say del CList at position 2. That works fine, and we can imagine now that this space in our memory is gone. Let me keep the thing there, the box. We can imagine now that this space in our memory is gone. But you can see that if you were to try to delete an index that is not the very last element, then we'd actually get an error. Can only delete the last item in constrained list. So we really are constrained, as it were, to only deleting the item at length of list -1, right? So those are the 4 things we can do with constrained list and nothing else. And this, again, is to mimic what a primitive array structure is like in other languages that have them. Python doesn't, so we had to build our own. Okay, so long as you use constrained list in your implementation, you can be certain you're not performing any illegal operations. If you invoke a disallowed operation, an appropriate exception will be raised. Be sure to evaluate the following cell before testing your constrained implementation, right? Or before testing your ArrayList implementation. Right, so make sure you run this, or else your ArrayList won't be able to see it, and so you won't be able to use constrained list. Okay, so the work that you actually have to do for this lab is all in the ArrayList class. And now for the task at hand. We've partitioned the ArrayList methods you need to implement, and the test cases that follow, into 7 categories. And here are the 7, right? So you can see, looking at these functions, these hash symbols denote the different categories. So if you're working on string and representation, that's short for representation, then this is all in the category stringification. And if you go down to the tests, you'll see that there's a set of tests specific to stringification. And if I run those after running my ArrayList, it'll tell me if stringification is not working, if just the tests in those things are not working. So you're more than welcome to jump around between these categories if one seems easier than the other, and you can test periodically on each one as you're going. Now, subscript-based access, you guys did together already in class. So these implementations should be done already. And if we run that and then test that first set, we go through and get no errors. So we're done with those. Nice job. So I'm going to go through all of these functions quickly and explain what their output should be, and maybe that can act as a guide when you're trying to figure out what you're supposed to be doing. So normalize IDX is just a helper function. It's defined for you no matter what, and you can use it any time that you might get a negative index. So you can see in get item, set item, and delete item, this normalize IDX is called so that if you get a negative index, it gets returned as the correct positive one. For get item, always pay attention to these comments here that explain what the function is doing, because it might not be obvious what's going on. Okay, so what gets confusing here is that we have to remind ourselves get item is a method under the class ArrayList, and it is under every iterable class. Get item gets defined for almost every iterable where you want to be able to use this notation, right? So let me show you what I mean. List is a class in Python. If I create some list, we'll call it named list, and it's got some elements. There's a few different ways I could get, for instance, the letter C. So I could do it the way that we're all used to, where I subscript named list at position 2, and that will output C. But I could also do this much more explicitly. I could say, go to the list class, use the get item method, self, which is just the instance that you're working with. This is the first parameter that we're passing, is named list. We're working on the list called named list that we defined up here. And the index, the IDX that we're passing, is 2. So 2. And if I run that, you'll see I get C. Or if I run it on 4, the last index, you'll see I get E. And so we're not used to seeing this function called in this way because it's much prettier, and intentionally so, to use the following notation where we say named list subscripted at whatever thing. And the same is true for set item. So if I have this named list here, and let's say that I actually messed it up, I put F here instead of E. If I look at named list and I realize, oh, I made this mistake, there's a few different ways I could fix that mistake. I could say named list at position 4 is now equal to something new, E. And that fixes our problem for us, so now our list is correct. But I could also say, if I run this cell again, and now it's incorrect, I could also say named list, no. I could also say go to the list class, use the set item method, our current instance self is named list, the index of the thing that we want to fix is 4, and the value that we want to replace it with is E. Now if I look at named list, E is there, and so we fixed it. So this method is exactly the same method that's being called when you do the following syntax, right? These two cells are doing identical things. And not to be overly redundant, but if I have this thing and I see that the F is there and I'd like to just get rid of it entirely, one way I could do that is by saying delete named list at that position, at position 4, and that will work. It's now F is gone. Or the other way I could do it, and entirely identically, is say go to the list class, call the del item method. The instance I'm working with is a named list, and the position, the IDX that I'm passing, is 4. I run that, and now F is gone. Okay, now on to the functions that are not defined for you. So in stringification, for the purposes of this, the string function and the representation function are actually going to be the same. It says that right here, same behavior as string. So once you have one of them working, you can your function can be exactly the same for the other one. The reason that we have two different functions is that String is typically used to output something very readable, and representation is typically used to show you what some data that's more useful for a programmer. It's like, to put it basically, it's like this should be what's user facing, and this should be what is programmer facing. This is more, you would define here the things or items that might be more helpful for debugging a program. But in any case, this is what happens whenever you call print on something. Named list, it goes to the string class, and I can say go to the list, call the string function on the instance named list, and I'll get back a string that is identical to what we just saw there. And the same is true of repr. I get the exact same string. On to single element manipulation. So if I have some string here, or I'm sorry, so if I have this list here and I'd like to add an e onto the end, I can say named list.append and e. So say we want to implement the append function for ArrayList, and the only functions that we have to work with are these four. Well, one thing we know for sure, we're going to need another space here, so we'll go ahead and execute list.append none, which will give us another empty space in memory at position 2 this time. And so right now, and so that's one thing that we've done. And then we know that we're going to take whatever value is passed to us here, and we're going to go ahead and put it in here. And then we can use one of the other four functions we have, getting and setting, to simply say that clist at position 2 is the passed value, right? We got passed a value. And so what we just did is break down this usually one-line function and down into the steps that comprise it. So for named list, which is a standard Python list, we can use append. And for ArrayList, we also want to be able to use append. But we have to define append, and we can only do these four operations. If we have some clist, which we'll pretend is a constrained list, and it's got A, B in it, then in order to abide by these rules, these are the only four things we can do. The first thing we would do is say clist.append none. So we've taken an empty box, and then clist at that new position, which is the very last element, the length of clist -1, 0 indexed. Whatever thing is there is going to equal the value that we passed. And so in your function, that will be value. For us, that's just c for the time being, just for the sake of example. And those things do the same thing, so ABC. Moving on to insert. So we see that our named list has the values A, B, D. We missed C, and so we'd like to insert C such that it is at position 2, right? Position 0, 1, 2, where D is currently, and we'd like D shifted down afterwards. So we'll say named list.insert at position 2, the value C. Our list, we'll see that C has been inserted here, and D has been shifted down. Pop is like delete, except whatever value you delete, you also return. And so if I wanted to get rid of D and also use it for something, I could say popped equals named list dot pop, and by default it's going to take the last element at index minus 1, right? So if I run this, I can now see that popped is the value D, and named list is now A, B, and D is not in named list anymore. The remove function accepts a value and removes the first instance of the value from the list, right? And then raises a value error if the value is not found in a list. So if we look at our name list here, you see we have A, E, B, C, D, E. Oops, missed a comma. A, E, B, C, D, E. So this E we don't want there, and so we can call named list dot remove the value E, and we'll see that named list has removed the first instance of E in our list. If we run that function again, we'll see that the second one has been removed because it's only removing one at a time, right? One of these values per remove call. But now we don't have an E in our list, so what's going to happen? If we run this function one more time, we get an error because the value that we tried to pass, the value that we wanted to remove, is not in the list. And so you'll be responsible for raising this error. And that's quite simple. We can simply say raise value error with some error message in here if we want to. There's our error message. And I don't think you're required to have any specific error message. In fact, I know you're not, but it might be helpful for debugging to do that, or to get in the habit of writing nice and thoughtful error messages. On to our predicates. So EQ is defined as returning true if the instance of ArrayList you're dealing with contains the same elements in the same order as the other. And if the other is not an ArrayList, it returns false. So if I have these two lists, list 1 and list 2, and they're defined to be the same thing, what this function defines is if this conditional statement, list 1, double equals, conditional equals, list 2, if this evaluates to true, that's what we're implementing. When does this evaluate to true? And if we were to change something here, it should evaluate to false now. If we were to keep all the same elements, but in a different order, it should evaluate to false. If we were to use some sort of different structure, like maybe instead of a list, we put a tuple here, and then even if the values are the same, we should get false because a tuple is not a list. And for the sake of redundancy, this is exactly the same as saying go to the list class, find the EQ method. The current instance we're working with, self, is list 1, and the other method that we're passing as a parameter, the other list that we're passing as a parameter, is list 2. Do these two equal each other? Yes, true. That's what you're outputting. If we have a list with ABCD in it, the contains method outputs whether or not the value passed as a parameter is in this list, right? And the common way of doing this, it's a conditional statement, is saying some value C in list. This is a conditional on its own, and if we evaluate it, we'll get a Boolean return. Is C in our list? Yes, it is. We expect to get true here, and we do. If we were to put a J, we would expect to get false because J is not in our list. And just to show you, this is exactly the same as saying go to the list class, use the contains method, check that the self, the instance that we're using, is the list. That's this name here, and the value that we're looking for is C, and that's true. On to queries. Length is quite simple. You're returning the length of list. Min, max are obvious. Index returns the index of the first instance of a value encountered between I and J. And we're asking, where in this list is the value C? Well, we might say list.index of C. And it tells us 2, position 0, 1, 2. But maybe you have more than one instance of the letter C in your list, and you're actually only interested in where the C's are in the last half of your list. I don't know, maybe. So you might say go from this first index, which is halfway through your list, or length of list divided by 2, it's 6. That'll give us 3 inclusive, sorry, up to just the end of our list. Say length of list. And what we'll get is 5, 0, 0, 1, 2, 3, 4, 5. So it returns this C, not this C, because we're only looking in these 3 items. Count is very simple. Okay, bulk operations, add, clear, copy, extend. So I'll go through these very quickly. So if I have 2 lists, 1, 2, 3, and 4, 5, 6, in list 1 and list 2, and then I add those lists and store it in a new list, we can now see that list is its own list. That's 1, 2, 3, 4, 5, 6. List 1 still has its elements in it, and list 2 still has its elements in it, and those are unchanged. So the list that gets generated by this add function is an entirely new list. You create a new instance of the object that you're adding with. And this is the same, again, as saying go to the list class, use the add method on list 1 and list 2, and and this does the same thing. Now extend is different. Extend mutates the instance of list that you're working on. So if I have list 1 and list 2 this time, so if I have list 1 and list 2 as the same thing, and I say list 1 dot extend list 2, I've actually mutated list 1. So list 1 now has the elements from list 2 stored inside it. So you're not generating a new list this time. List 2, however, does remain the same. If I have a list 1 equals 1, 2, 3, and I say list 2 equals list 1, and I run both these lines, you'll see list 1 is, of course, 1, 2, 3. List 2 is, of course, also 1, 2, 3. But what happens if I change list 1? Let's say I say list 1 at position 0 is now going to equal A, right? So if I look at list 1 now, we have A, 2, 3. So list 1 used to be 1, 2, 3. List 1 is now A, 2, 3. But remember, I did this. List 2 equals list 1, or list 2 is being assigned to list 1. So do you think I changed list 2 there? Let's see. I did. I changed both, because by doing this, I've not only said I want this to have the same values, but I've actually said I want list 2, this variable, to reference the same place in memory that list 1 does. And so we get this change in output on both. So what if, instead of having list 2 reference the same place in memory as list 1, I just want it to have the same values, and I want to be able to change them independently? Well, that's what the copy method does. And now, instead of saying list 2 is equal to list 1, I just want to copy it, and so I'll say list 2 equals list 1 dot copy. Excuse me. And now, if I change, so I see list 1 and list 2. Okay, list 1 is that. List 2 is also that. But now I'll change it so that list 1 at position 0 equals A. And now if I look at list 1, I can see that change has been made. And if I look at list 2, that change hasn't been made, because by using the copy method, I have fixed the problem of referencing the same place. I've created an entirely new instance of the list class. So when you implement the copy method, you're, like it says here, returning a new ArrayList instance. And finally, the iter function that allows for iteration. Now, if you go to the course website, mazda.csit.edu/CS331, you'll see that there's a whole notebook down here. Where is it? Implementing iteration, which is dedicated to talking about various ways of implementing this iter function, right? There's a whole notebook for them, so I highly recommend going through it. But briefly, the behavior that you're defining here is what allows us to do things like use a for loop on a function. So if we have a list here, A, B, C, D, our iter function gets called when we say for item in list, right? We're calling iter here. It's returning, it's creating a generator for us of this list item, right? And we get A, B, C, D. And so you can see this is exactly the same as calling iter on list will give us exactly the same output. It's also exactly the same as saying go to the list class, use the iter function on the current instance list, and we'll get this same output again. I can run that a few times, A, B, C, D. So that is what is expected of you for each of these functions. Another quick note on how you might do this. We strongly advise that you start with the first category of functions and move down the list sequentially, pausing after each to run the corresponding test cases. The only category that might be worth skipping to early on is iteration, which can help simplify several other methods. If you've made one of the functions here, you can use that function in other functions if you think it would be helpful. And what we're saying is that it might be especially useful to define iter first before you do any of the others, because that'll allow you to do to more basically go through the list and get all the values, because right now with constrained list you can't by default, right? So consider starting here when you do this. There's an example of this. For instance, your implementations of pop and remove can and should use the del operator. Use the del operator on your own list to remove elements from the middle, and it probably makes sense to use extend in your add and copy methods. Okay, that is it for Lab 4. As always, if you have any questions, please go to Piazza and ask them. Our average response time is 10 minutes. Also, go to office hours, please. Okay, good luck with Lab 4. See you next time.